Hello, everyone. Welcome back to Bang Bang Con session number 2. We just wrapped up our hallway track. It was a lot of fun. Skittish looks like an interesting space. It was really cool to see all the little animal avatars interacting with each other and so many different little conversations happening everywhere. So it was great fun. We'll be continuing to use Skittish for our other unconferencing sessions, as well as the hallway tracks in future dates for the rest of the week that we're here at Bang Bang Con. So I guess we'll go ahead and wander into our next speaker. Jade Fink is doing frontline teaching in Elf to Uwu. Jade is a computer engineering student at the University of British Columbia in Vancouver. While she's not hacking on tooling, primarily Rust, operating systems, or making jokes on Twitter, she likes to bake and go on long bike rides around the city. So I believe Jade should possibly a recording, I think. So we can go ahead and pass it over to Jade.
Hi, I'm Jade, and today I'm going to show how to turn println into pointln. You can find a link to these slides on the bottom left. This idea was inspired by my friend the 6B4C on Twitter, and I've further developed it into a crate called pointln that is available on the crates registry. This talk demonstrates the prototyping process that went into that crate. This is Coralie and Safer Station. You'll be seeing some more of them in the slides. They're a friend. So I remember reading about a binary exploitation technique where you could overwrite some function pointers in memory and get the program to go elsewhere when functions from external libraries such as the systemc library libc are called. Let's try writing a program and see what we can find of those. So we're going to make a string hello bang bang con, and then we're going to write it to the screen. So we're going to use the write call, and we're going to pass file descriptor number 1, which is standard output. And then we're going to give it a pointer to our string. We need to turn that into a void pointer, so let's cast that. And then let's give it our string's length. Then we get an error that we need to use an unsafe block, so let's do that because raw pointers are unsafe to use. And now let's compile and run our program. Let's look at it in a debugger and see if we can find those function pointers we're looking for. So we're going to set a breakpoint at the start of our program. And then we're going to disassemble our program. So we see at the bottom here a jump keyword pointer RIP plus some offset. The square bracket syntax there is a pointer dereference. So it's dereferencing the pointer 39599 bytes after the current instruction. So if we look at what's actually there at address 555 whatever, then we see that there's another pointer. And we find that if we look at what's at that pointer, we find it's a pointer into write in the systemc library. So that's what we expect to see. However, how would we find this address? So in order to answer that, we need to look at what an ELF is. So an ELF is the executable format used by Linux and BSD. It loads various sections out of your executable into requested locations in memory with requested permissions. And it also allows for dynamic linking, which means that you can have libraries that you can replace without having to recompile your program. How do they do dynamic linking? So on Linux, dynamic linking is accomplished by the dynamic loader, which gets at your program before you get control, and it will load all of your dynamic libraries and set relocations of all of the functions that you call in those dynamic libraries to pointers to the actual functions in memory. So we want to read a relocation, and for that we're going to use readelf. So let's try that out. So we're going to read the help page for readelf and see if we can find something to do with relocations. And indeed, we have -r, which deals with relocations. Okay, so let's try looking at that. So we're going to go look at the relocations of our executable and search for the write function in glibc. We find that it is indeed there and it is at some offset. We don't necessarily know what this offset is for yet, but let's guess that it's probably from the start of our program. We can find the start of our program by running infoproc mappings in GDB. What this will do is it will find all the regions of memory that our program owns, and we see that this top one is at offset 0 of our executable. So that probably confirms our hypothesis already, but let's continue testing it. So we're going to add the offset that we got from readelf to the number we got from GDB for the base of our program. And then we're going to dereference that as a pointer. And we see a 7FFF value that we saw before. So that already looks promising. And indeed, if we look at an instruction there, we see that it is part of the write call. So that's good. Let's start writing a wrapper. So this wrapper has the same signature as the write function in libc, except it's translated into Rust syntax. First, to wrap this, we need to turn our input into a slice of bytes. And then we take that slice of bytes and then we turn it into a string. So it's a reference to the string that we were given. Then we convert that string to UTF-8. Well, strings are UTF-8. And then we need to copy that into heap memory as an own string and then AWOIFY it. So now we have an AWOIFIed string. So now we need to write it to the screen. However, since we are going to overwrite the pointer to the write function, we have to store away its original value because we can't call it through its normal method. So we're going to make a global variable that we're just going to store the address of the write function at. So in our wrapper, then we are going to use that global variable to call the write function, the original one, with our AWOIFIed string, with the same file descriptor, and with the AWOIFIed string's length. We then have to lie to our caller that we have written exactly how much they've asked for, because otherwise it will go badly if we say actually wrote more than they asked for because we added some characters while AWOIFYing. We then have to also add our AWOIFIcation library. Next, we need to overwrite that function pointer. So we're going to take in the hex address from the command line that we had gotten from readelf, and then we're going to add that to the base address of our program that we got from before. Next, we're going to dereference that pointer and overwrite it, but first we have to store it away in our global variable. So we're going to use memtransmute, which what that does is it converts a value of any type in Rust into any other type. It is extremely unsafe and therefore a lot of fun. So we turn the dereferenced value of the relocation, that is to say the address of the actual write function, into a function pointer and then store it in our global variable. Then we overwrite the relocation with our replaced version. Then we rebuild the program. We redelf it again because it's possible that the relocation moved because we added a bunch of code. Then we get the address and we set it as a command line argument with set args. And then we run our program. Unfortunately, it does a segmentation fault. Let's see if it is at least doing what we expect it to do. So the address that we have is 555 something, which is what we saw before. And if we look at what's at that address, we indeed see a function pointer. And if we look at what's at that function pointer, indeed it is a function pointer to write. So it is what we expect it to be. But the reason it failed is because, as I said before, the ELF format allows you to specify permissions for regions of memory. And so the relocations region is actually read-only, and therefore our write to it failed. So all we have to do is we have to tell it that, like, actually we do want that to be writable. And for that we use mprotect. So what we're giving it is the address of the bottom of the 4096 byte page or region of memory that the function pointer that we're trying to overwrite is at. And then we ask it to change an entire page at once. The reason for this is that the granularity of memory permissions is one page. We do some bit tricks to get the bottom of the page. Then we go to readelf again and go and get the right offset for our modified program. And we set the arguments and we get hello uwu con uwu. Yay! All right, so this also works on println because println internally calls write. How do we do this properly though? It turns out you're not actually supposed to redirect control flow of programs, and generally that's considered a security vulnerability. So there's various mitigations that are used to stop people doing this. One example is layout randomization. The program is not normally loaded at OX555. It is loaded at a random address that changes every time. which means that shenanigans like this aren't supposed to work. It only works because it's in a debugger. The other thing is that the relocation section that we're trying to overwrite is write protected, which is called relrow, relocations read only. We also want to find the symbol ourselves, and that's how we would get to like what the pointLn crate does. How do we start at finding the symbol? Well, we want to look at readelf output, and we find that we have this relocation section relay.dyn, so we need to find where that is. And so with this convoluted page of diagram that was made from reading man5elf for a long time, we can find the symbol by looking at our program information. So the starting point that you would use is getOxval, which looks at information that the kernel returned while loading the program, and that will tell us where our program headers are. And then from that, that's just the executable that's mapped directly into memory. So then you essentially read the elf file as if it was on disk, but just like out of your own memory. You look at the program headers and use those to find your program base address and also where the dynamic table is. From the dynamic table, you know where the relay table is, where the symbol table is, and where the string table is. From the relay table, you go through each entry, and then you can find the symbol table offset of each entry, use that to index into the symbol table, and then that will tell you the string table offset of the name of the function. You go through all of the relays until you find right, and then you know what your offset is, and then you can implement pointLn. So this is very close to what pointLn is that we've already built in 10 minutes. So that's all I have. Enjoy the rest of your Bang Bang Con.
All right. Thank you, Jade. That was wonderful. I love the talks that pretty much are like, you should never do this. This is an absolute problem. I'm going to do it anyway and rip apart things that shouldn't be ripped apart.
This only works on a debugger, you know, but why not ship some stuff to production? That happens to everyone, right? Like, it works on a debugger. Let's make it work everywhere else. I'm happy that you're mindful of it not being the right solution for anything but playing in the debugger.
Yes. And, Bang Bang Con is like the perfect place to just do silly things like that because it's fun and it's the surprise of computing, I suppose.
Yeah, and it's cute. The output is cute, so we love it.
Definitely. Thank you, Jade. If you wish to reach out to Jade, you can reach out to her on Discord in the channel, or you can reach out leftpad.py on Twitter. Our next speaker is Nathan Kisman, doing Bang Bang, hacking Switch controllers to play rhythm games using a real drum. Jonathan is a software engineer at Orbit by day and live production tech, pyrotechnician, and musical theater performer at night. I would love to see some of this. His interests include hardware reverse engineering and information security. He has once set a swimming pool on fire. I feel like you all need to ask about this in Discord. So here's Nathan to give our next talk.
Hey there, I'm Nathan. That was not my description. I wish I have set a swimming pool on fire, but that was actually for someone else. Anyway, I'm Nathan, and I play the drums. Well, more specifically, the drum. A year and a half ago, I joined a taiko drumming club at my school. Taiko is a Japanese word meaning drum, but it usually refers to playing many chudaiko, or fat drums, in a small ensemble. I absolutely love it, mostly because I get to play very loud music for hours on end, and I don't have to worry about learning things like chords or scales or any of that music stuff. However, due to my school being closed, I haven't been able to play with my group in over a year. Luckily, Nintendo has come to the rescue. Originally an arcade title, Taiko no Tatsujin for the Nintendo Switch is a rhythm game where you play taiko. But unless you can find the arcade version or pay extra for a fake drum, you're stuck waving the controllers around in the air, pretending to play a drum, which is not nearly as fun as wailing on a real one. My first attempt to improve this made it feel somewhat more realistic, but it was pretty crude, it missed a lot of hits, and it just didn't feel quite right. However, since I have a real drum, why couldn't I make something so I could play with it instead of the controllers? So to do this, we need something that can listen to the drum using a microphone, translate it into button presses for the game. This is where the mighty microcontroller comes in. A microcontroller is a chip that contains a processor, RAM, program storage, and interfaces for other electronics. It's the perfect tool to take in signals and event from electronic hardware and act on that data. They're absolutely useless on their own, but can be connected to anything that uses electricity and a lot of things that don't. The most famous microcontroller is the Arduino, made famous by maker blogs around the globe. It's a great board, it's very low power, very simple, but the chip in many of them is 15 years old, so it's pretty slow nowadays. For this, I use the Teensy. It uses the same code as the Arduino, it has compatible libraries, but it also has a ton of new libraries on top to interface with more advanced hardware. It's super fast, it can emulate all kinds of USB devices, it has great support from its creator, and it's teensy, it's very small. Another board is the RP2040 by the Raspberry Pi Foundation. It's more powerful than the Teensy at a quarter of the price, but it's brand new and had only been out for a few days when I started this, so I didn't use it. I also could have used a regular Raspberry Pi or the Raspberry Pi Zero. These are great if you need to do video or talk to the internet, but it is a tiny computer, which means you have to deal with all the not so joyful parts of computing, like updates and long boot times, as opposed to these, which directly run processor instructions without an OS getting in the way. So first we need to get audio data from the mic in the form of an analog voltage waveform into the Teensy. And to do this, I use another one of my favorites, the Teensy audio board. This adds a microphone and headphone ports to the Teensy, along with an SD card slot for sound files. It's also built to be compatible with the Teensy audio library and its audio systems design tool, which is one of my favorite programming tools ever. This designer gives you a bunch of input, output, synthesizer, filter, and analysis blocks that you can connect together graphically, and it even tells you how to use them. Then, once you're done designing your layout, you click export and it gives you a code block to paste into the beginning of your program, and it just works. It's super powerful, especially for a board as low level as the Teensy. So for our application, if we needed to detect just any kind of loud bang, we could use simple peak detection like shown here. However, Tycho uses both hits on the center of the drum, making a low bass sound, and on the rim of the drum, making a higher pitched tack sound. So we need to be able to differentiate and detect both these kinds of hits based on their pitch. To detect pitch, we need to use an FFT, which stands for a fast Fourier transform. What's a fast Fourier transform? Well, it's like a regular Fourier transform, but just way faster. Fourier transforms are a very deep subject, but for our simple use case, we're taking small slices of time. This library uses 344ths of a second for some reason, and using it to tell us what frequencies or pitches are present in that slice of time. This method gives us an array of 256 floats, each index representing a bin 172 hertz wide, and the percentage of the sound that fits into that frequency bin. So, using one of the examples included with the library, I made a test program that listens to audio from a computer over USB and prints the FFT arrays to the console whenever it hears a sound. Then I recorded some drum hits and I played them back, so I'd have a repeatable signal and wouldn't have to go back to the drum and smack it every time I recompiled. So here are some representative hits along with their corresponding FFT readouts. Looking at this, I noticed that hits on the rim never have any frequency in this bottom bin, whereas hits in the center have tons of frequency in this bottom bin. So my code gets to simply wait for any kind of audio spike, check that line of the FFT, and print center if it sees sound in this bottom bin right here, or rim if it doesn't. That's all we need to detect and differentiate between these two kinds of hits. So now that we can detect hits, we need to actually complete the other half, that is pressing buttons within the game. Since the Nintendo Switch uses USB controllers, and as we know, the Teensy can emulate USB devices, I thought it could be done over USB. And sure enough, I found a library that does just that. So I installed it, and that does not look good. So, turns out this library doesn't quite implement USB correctly and basically undefines all print statements, causing tons of compiler errors. So I did what any rational programmer would do, and I commented out all 854 print statements from the standard libraries. Typical coding stuff. This made my code compile, yay. However, shockingly enough, it still didn't work. So I did what any rational programmer would do again, and I went to Target. And I bought the cheapest controller I could find. After all, if we can't emulate the controller, we'll emulate the player. I got this in response when I shared my improvised plan with a friend, and personally, I think this is electronics in a nutshell. Cracking the case open, we can see that this shoulder button right here is connected by easy-to-access wires, shown here. Using an ohm meter, I found out that every time the button is pressed, it connects the ground of the controller to the processor inside of the controller. So if we connect our teensy to the wire as well, it can simulate a press of the button by putting a low or 0-volt signal on that line, essentially connecting it to ground like the button does. So I wired it together. I modified the code to press the correct button when it heard a drum hit, and I hooked up this mess of wires to my switch, which not only didn't catch fire or break, but it actually started responding to the fake button presses. So I changed the input in the code from USB audio to the line-in jack. I soldered in a microphone jack to the board. I hooked up my microphone, and I tried it with my drum. I love those corgis. So if any of you play Taiko, please don't mention my terrible form to everyone else. Hopefully we can keep that a secret between us. Anyway, this works surprisingly well without a lot of tweaking. I think it was helped a lot by this game being designed for motion controls. So it's pretty lenient with double hits or hits that are too early or too late, which I guess I accidentally took advantage of. So although I don't think many of you will go out and buy drums to recreate this, I hope this can serve as inspiration for future projects of your own. I usually like to modify hardware and tack on my own electronics like this instead of making things from scratch, usually because I can use their existing power supplies and enclosures and interface, so there's less for me to do myself. In this case, I would have had to make a controller from scratch, which I have no idea how to do, or worse yet, make my own game, and wow, have you seen how much effort that takes? Plus, it's fun to share mods of games and hardware with folks because you get an instant level of understanding with them when you proclaim, I did X with Y, which is pretty nice. However, this means that there isn't a full understanding of everything in the system, which can make troubleshooting a lot more painful if something goes wrong. I usually just hope nothing goes wrong. If you want to do more hardware hacking or making stuff like this, great places to get inspiration and help include Adafruit and SparkFun, who make electronics for hobbyists like myself. And they publish tons of project guides, tons of how-tos, and they even open source all of their hardware and software design. So they're really great companies, really great resources. Hackaday.com and Make Magazine also has a tons of inspiration for projects like this. Anyway, that's it from me. I hope you enjoyed, and thank you so much for your time and attention.
Thank you, Nathan, not Jonathan. So we're going to fix my little error. Nathan is a student at Columbia University, go Lions, studying electrical engineering and computing history, and is also president of the CU Taiko Club. When not working on problem sets, he's generally exploring retro tech, enjoying long walks on Maine's beaches, creating and sharing art, and wandering aimlessly around the World Wide Web and telling terrible jokes. I can appreciate that. One project he's working on right now is documenting X-Band, a defunct and recently resurrected dial-up network for the Super Nintendo. I definitely love hardware hacking and playing around with things, and so I appreciate this talk on a very
I
hacky
tried
level.
playing Taiko with Switch controllers, and it was pretty bad. I'm gonna blame it on the controllers, not on my rhythm skills. Though my partner, who is a drummer, didn't have the same issues, so shh.
I won't tell anyone. Neither will you, right? Like no one. This won't get out
no one knows.
past just us. Yeah.
Yes.
And it kind of reminds me, a couple years ago, Sophie Daisiel gave a talk about building like a little robot to play Pokemon on her Switch, I think. So that was kind of reminded me a little bit about that too. I love fun hardware hacking things in ways that you just don't expect.
Yeah, and also the advantage Nathan got from actually making using the delay in the sound to his advantage in the game. I love that.
Yeah, very smart, very creative. I
Would be
like it.
useful for me.
Thank you, Nathan, not Jonathan, for your wonderful talk. If you wish to reach out, there's obviously the Discord channel for the talk, but also you can reach him at inkiz11 on Twitter. Up next, we have Patrick Stefaniak, who's doing crocheted computer graphics. Patrick is currently an MFA student in digital art and new media at UC Santa Cruz, earned a BFA in digital art from Indiana University in 2015, and has worked in New York as a creative technologist. He works with 3D games, virtual reality, video performance, installation, writing, hole punching, crocheting, and 3D printing to think about rendering, perception, labor, queerness, and fun. It's a very good combination of many things. Here's Patrick for his talk.
Hi, my name is Patrick Stefaniak, and I'm currently an MFA student in digital arts and new media at UC Santa Cruz. And my talk today is Crochet Computer Graphics. I'll talk about my MFA thesis, Cloth Cubed, and why I think it's interesting and useful to think about textiles and computer graphics together. I started crocheting after reading about the Crochet Coral Reef, which is a communal project started by the Institute for Figuring. They ran workshops teaching participants how to crochet using a simple method of adding a stitch in a regular interval to create forms that are geometrically accurate models of hyperbolic geometry that also resembled coral. What I found useful about this was a method for rendering forms that was both mathematical and biological, that used a single, simple technique that through small variations can produce wildly different shapes. It also removes a sense of correctly creating a form, as an irregular stitch can become a seed for an interesting variation rather than just being a mistake. I was also interested in a paper written by Jean Vaccaro, Feelings and Fractals, Woolly Ecologies of Transgender Matter, where she does a reading of this project along ideas of trans aesthetics and practices, which proposes craft as a way of thinking about the daily practice of maintaining and constructing our bodies and identities. Another paper by Victoria Mitchell titled Drawing Threads from Site to Site discusses how textile production is integral to how we construct and perceive space. A piece of cloth starts out as loose fibers, which are then spun or drawn into a line of yarn, which is then woven into a cloth. Reading this, I immediately connected that sequence to the process of constructing a 3D model. A set of points in a space are connected by edges, which join into faces, which close up into 3D shapes. In doing more research, I learned that the history of computing is also entwined with textile production. One of the earliest working computers was the Jacquard loom, a weaving machine which uses a series of wooden punch cards to determine thread patterns. Also, early computing used to involve a lot of hand wiring of circuits and was considered a feminine task. It wasn't until programming became a less physically oriented task that it began to have the masculine associations it still carries today. Cloth Cube interacts with all these ideas by focusing on different methods of rendering a cube made of cloth, either by crocheting or by using cloth simulation tools in Blender and Unity. There are 3 pieces in the show. Unity Primitive Cube, a 2-scale crocheted rendering of the standard cube in the Unity game engine, which measures 1 meter cubed that can be picked up and held by the visitors. A few ways of being a cube, a grid of 64 3D prints of cubes that have been deformed through cloth simulation, and it's meant to be looked at and not touched. And Cubism 2 Baroque Edition, a video game which has digital versions of both of the other 2 sculptures that can be played with in a variety of ways. As an installation, it's played on a touchscreen and also projected onto the wall, but there's also a desktop version that is downloadable on itch.io. order to access these ties between textiles and digital graphics, I focused my work on using the cloth simulation tools in Blender and Unity. This is an ongoing interesting problem in computer graphics where the goal is to create realistic cloth movement. The basic method is by considering the 3D geometry as a mesh of nodes which stretch and compress in relation to one another based on a complex set of rules. The project focuses on tools that are easy and available to use because I'm more interested in working on them with my hands through the interface rather than trying to build my own mathematical models. Each of these pieces in the show renders the same cube in different scales, techniques, materials, and modes of interactivity. Digital graphics are hard to understand because the way that they're created is obfuscated by the machine and the high resolution of the screen. When you look at the crocheted or 3D printed cubes, you can see the stitches and the lines of filament that are accumulated to build up the shape. You can picture what the labor looked like and know that you could learn how to create similar objects. By repeating these cubes in these three formats, which are digital and physical in very specific ways, I hope that the viewer can gain a material, hands-on grasp of both the technology and the theoretical and art historical references, which mainly come from the minimal and Baroque art. Baroque art, like the music of Bach or the sculpture of Bernini, was characterized by virtuosic performances of specific sets of rules. As you can see, cloth simulation has been an interesting and difficult problem for a long time. Today we have computers which are great at following rules. My ability to play piano or sculpt delicately are far exceeded by what code can do. My hand is still present in playing with these tools and selecting outcomes that are interesting to me. None of this has been fully decided by an algorithm. I can relieve myself of the pressure to perform correctly and allow myself to create in ways that I find joyful. Minimal art is characterized by simple shapes, which typically attempt to avoid representational references, and by serial modes of production which are often outsourced to be manufactured by people other than the artist. In these ways, it's remarkably similar to digital art, where the computer does the work of rendering and favors multiples, variations, and basic geometry. I especially find useful how minimalism draws attention to the viewer's bodily relationship to the object, which interaction design tries to eliminate in the name of a seamless user experience. Fabricating a giant steel sculpture is expensive and difficult, but with projections and VR headsets, we can quickly recreate similar forms that can be displayed in a larger variety of contexts. My video game making practice has been greatly influenced by ideas from queer video game design, especially the ethos described in Rise of the Video Game Scenesters by Anna Anthropy, about approaching games as zines in terms of their DIY production and distribution. This allowed me to think about other forms video games can be modeled after, like a painting, sculpture, or video installation, which each has their own standards of being made, shown, and sold. Thinking about game design as a textile craft similarly allows us to shift the frame of how we approach using these tools and what is considered a legitimate work. Unity Primitive Cube was made using one basic stitch that was repeated thousands of times. Cubism 2 Baroque Edition is built as an accumulation of short vignettes, each with a different way of interacting with the cubes on the screen. Because the scenes are separate from one another, I'm free to reuse or reconfigure code and assets in ways that would be seen as inefficient in standard game design. This relieves many roadblocks that are encountered in programming and game design, where a large, seamless game has to have many parts that work in unison. Instead, I get to focus on one action at a time. When that piece is done, I don't have to keep going back and fixing or updating it. Instead, the question becomes how to sew the pieces together once they're all finished. I believe that anyone can learn how to use complicated software like Unity or Blender. The problem is in how to feel comfortable getting started. Just like teaching someone how to crochet, I think it's a matter of sitting with people and showing them how to do that first basic stitch, like adding vertices to the initial Blender cube or placing objects in Unity to look at them with the first-person controller. With that one fundamental action, you can create almost anything.
Thank you, Patrick. That was really interesting. I love seeing cool visual things like that and sort of the background of how they work and how they kind of come together in ways like that.
Yeah, and I'm especially excited as someone who crochets a lot and does a lot of knitting, as do a lot of people who are on Discord. We even have a channel for all the makers and crafters. So, watching a talk about crochet web crocheting, I don't think it gets better than this.
Yeah, definitely. And I know I've talked to several friends that are also somewhere in the tech field, and they've said, crocheting and knitting are super easy to pick up because there's just a lot of simple logical patterns that are just, because a lot of the nature of what we do in tech is kind of also working with simple patterns and things like that.
Yeah, and it's interesting to see how you can make them more similar to the natural world with, tweaking a bit and looking how different shapes emerge. So I really enjoy that.
Yeah, definitely. So thank you, Patrick. Pseudo Pat is his Twitter name. You're welcome to reach out to him, or obviously on the Discord channel. We have the channel for that. It's also really refreshing to see all the clapping emojis just scroll off screen every time somebody's finished a talk. I just love the vibe that Bang Bang Con always has. Also, this is Theodosius. We were talking earlier about having on-stream pets. This is Theodosius. He loves helping out by cuddling me, climbing on keyboards, and just like rubbing me to death. He's my extremely giant
That is one big cat. It's like both of my cats together in one cat.
Yeah, and I have his brother. He's sitting over here. Together, it's like 35 pounds of cat.
That's a lot of cat.
Yeah, it's ridiculous. So would you like to read the next speaker? All right. Richard Schneeman is giving a talk called Beware the Dreaded Dead End. Richard is an open source junkie that loves community building. He created and maintains codetriage.com, a tool for helping people contribute to open source. When he's not working on that, you might find him building developer tooling at Heroku or working on his own open source contributions. He's in the top 50 Rails contributors and is an accidental maintainer of Sprockets and Puma. Last time he checked, he had over 1.2 billion library downloads on Ruby Gems. When he isn't obsessively compulsively refactoring code for performance, he spends his time reminding his kids to wash their hands. Good thing to do in a pandemic. Let's welcome Richard.
All right. Hello, everyone. I am coming to you live from. Wait a second. You hear that? You hear that? Everyone, run! Okay. Oh, there are more of them. More of them. Everyone, save yourselves. Okay. All right. Okay. Whew. Okay. Wow. I'm so glad we are all safe. I am so glad we're all safe. My name is Richard, and people like to tell me that I am an exceptional programmer, largely because my programs, they generate a lot of exceptions. I love exceptions, though, especially when they help me. For example, this is beautiful. Okay, name error. Did I mean to use chdir? Yes, I did. Okay, this error, it brings me joy. But what about this code, huh? Syntax error. All right, where's the syntax error? It says it wasn't expecting an end. Okay, but where's the problem? You might as well just throw up a giant sign that says dead end. The error points to the last line, but the problem is actually on the first. I'm missing a do here. If you're not familiar with Ruby's syntax, here are keywords that can trigger a required end. If you have an end statement that doesn't match a valid keyword, it triggers a syntax error. The trickiest one of these is do. In Ruby, do starts a block. This is valid Ruby code. chdir with a block changes the working directory of the process. chdir with a block also changes the working directory of the process, but switches back once the block is done. If we remove the do from the source code, it generates a syntax error. And so any method can take an optional block. You can pass a block to just about any method. When you get a syntax error, Ruby will tell you that the problem is at the bottom of the file, no matter where you're missing a keyword. It's not helpful. It's very confusing. We're gonna fix this dead end problem. So first, I'd like to tell you about a scientific study I did on time lost to syntax error exceptions. I found the average developer loses about 100 hours of productivity due to these errors. When I asked developers what they wished for most in life, 78.3% of them told me that they wanted an AI algorithm to tell them where their syntax errors are. So let's do that. First, though, how does a computer convert text into a program? All right, well, you start off with some code, like here's just a really simple string, it's hello world. The programming language passes your source code to a lexer. Ruby ships with a parser and lexer, which is pretty sweet. It's called Ripper, which to me sounds like something from an album cover. Could be a band. It's pretty sweet. Ripper takes the source code and then converts it into tokens with significance. It will tell you the type of the character at the start of the string is a double quote, and the contents are hello world. And so we can use this lexing technology to tell us whenever our source code has a keyword in it. After the source code is passed through a lexer, it's then fed to the parser, where those significant groups are turned into a syntax tree. All right. There we go. So this Ruby source code generates that syntax tree. At this stage, we can detect syntax errors. If we try to comment out a critical line, then our parser will generate an invalid syntax tree. An important trick that we're going to use later is that if you keep commenting out lines from invalid source code, you'll eventually be able to build a valid syntax tree, which also means that your code is valid. Okay, let's switch gears though for a second. Who here knows what AI is? Raise your hand in your homes. I can see. No, I can't see you. Comment something. Say me emoji. I don't know. I don't see anything. Nobody. Real hat. Yes. Yes. This is live. Okay. Nobody knows what AI is. AI is artificial intelligence. It's a fancy word of saying. Oh, there we go. Algorithm. Oh, come on. No, you're not. Fine. Okay, so more specifically, AI is a goal-seeking algorithm. A common example of AI is pathfinding. You want to get from point A to point B. How would you tell a computer in order to do this? You need a way to break down the problem into discrete actions that either get you closer or further away from the goal. In pathfinding, that would be deciding what turns to take, what roads to drive on. And then AI also needs a goal. It needs to know when it can stop looking. For driving, the algorithm stops once the destination has been reached. Now, we can blend these two topics together. We start with bad source code. First of all, what's our goal? Our goal is to transform the source code until it can parse again. Once we've done that, we can stop searching. We know that the syntax error has to be within those lines. We can use our lexer to determine if our source code has a keyword. There's one other thing, one other piece we are missing, which is intent. So how does source code convey intent? What's a way? This code here is ambiguous. The end on the very last line could belong to either line above. One of these lines is missing a do, but we don't know. It's impossible to know. This code, on the other hand, is a little bit more clear that the developer intended line 2 to be a block due to the indentation. Source code. Oh, sorry about that. That's where our do goes. So indentation is going to carry programmer intent. At this point, we've got all of the pieces that we need. Okay. This is real Ruby source code with a real syntax error in it. It's organic syntax error. We will use the dead end gem in order to find the problem using the tools that we've discussed. All right, the algorithm finds the largest indentation with 10 spaces on it. It finds the last of those lines and works its way up. Here we've hit a change in indentation. All the code is valid. We're going to check it with Ripper. We know the valid code cannot contain the syntax error, so we can comment it out safely. This block is going to be added to our frontier for future expansion and exploration. There's still more large indentations to explore before we can revisit the frontier. This line is valid. And that's it for code with 10 indentations. So now what? Rather than start exploring the 8 indentations, we can pop a code block out and expand it. These lines were generated when code already on our frontier were expanded up and down. When that happened, our lexer saw that we hit a keyword on line 51 with the if and an end on line 60. And so it pauses and checks it. It's valid. We can add the expanded block back to our frontier. We popped the same block, expanded the same block. It hit a change in indentation. Repeat again. We stop do an indentation change again. And at this point in time, the AI or algorithm has successfully found a valid lexical block that starts with def and correctly ends with an end. We could keep expanding that block, but we've got other unexplored code at higher indentation now. We go back to our add phase. Valid again. Keep looking. See the problem yet? Anybody? Okay, back to our frontier, expanding blocks up and out. Again, the code here looks dangerously suspicious. What happens when we remove it? Right, syntax is okay. Great, so our goal-seeking algorithm successfully found the invalid syntax nodes and removed them. It can stop searching. We then present these findings to the user. This is the actual output that you get from inputting that file into dead end. There are extra lines on 38 and 45 added in for a little bit of extra context and to accommodate an edge case I don't have time to fully go into here. Since release, Dead End has been downloaded over 144,000 times and counting by exception connoisseurs. And today we talked about lexing, parsing, syntax errors, syntax, AI, pathfinding, goal seeking. But really though, I just want to take a second and just think about the non-technical pieces. The technical pieces aren't really what I want you to focus on. The important thing for me is that everyone sitting in this virtual room together is the future of developer tooling. Programming is inherently difficult, but it doesn't mean our tools can't help us. One of the best ways to judge a system is to see how it fails. When we give care and grace and beauty to our failure modes, then we can create experiences that delight us, experiences that teach us, experiences that elevate our code and our consciousness. A syntax error doesn't have to be an ending. It can be a beginning to a beautiful programming story. My name is Richard Schneeman. I go by Schneems on the internet. I created CodeTriage.com. Easiest way to get started contributing to open source.
I want you to go forth and be an exceptional programmer. Bye-bye.
Zoom wave, everybody, Zoom wave.
Oh, are we not all supposed to run from the dinosaurs? Yeah. Thank you, Richard, for that interesting talk. I love kind of the idea of, we all call Mount out code, but I kind of love the idea that we've found an interesting way of kind of like navigating the context of things we mess up in our code and kind of fixing them more dynamically.
Yeah, I especially related to this talk because as someone who works as an SRE/DevOps in a Ruby company, I don't really write Ruby a lot. So every time I see this error, I feel the pain and I am terrified. So it makes me happy that there are delightful tools you can use. And then they actually help you become, more of an exceptional programmer, because once you find an exception, you can find another exception. That gives you more time for exceptions.
Yeah. Yeah, it's great. Thank you, Richard, for that very interesting talk. And we all loved your special effects, possibly the most special effecty talk I've seen in a long time.
Yeah, it was hard to focus on the content. It was so good, but you still managed to get us to learn something. Thank you.
All right. This wraps up session 2 for Bang Bang Con. Thank you all for joining us, whether you've been live streaming on YouTube or watching in any other way, whether you've been hanging out with us on Discord or in Skittish or wherever you've been joining us. Thank you for doing that. Special thanks to our speakers today. We've had Angie Jones, Phil Salvador, Aaron Reed, Pokey Rule, Lynn Pepin, Jade Fink, Nathan Kisman, Patrick Stefaniak, and Richard Schneeman. Also, special thanks to our captioner, Lydia Perez, who's been doing a great job of keeping up with everything going on here. Our captioning is done by a real human behind a real screen listening to everything that's going on. So thank you for that. This wraps up today. Our next sessions start tomorrow at 8 p.m. Eastern, 5 p.m. Pacific, and 1 a.m. UTC for all, or British time for all those night owls. If you missed any of these talks or want to watch our rebroadcast, the Sync Watches start tomorrow at 6 p.m. British time, or 9 p.m. or 9 a.m. Pacific, or 1 p.m. Eastern. Don't forget, we'll have unconferencing later this week. You can find the link to proposing some unconference sessions on Discord in our announcements channel. Until then, on behalf of all of our Bang Bang Con organizers, thank you for joining us, and we'll see you tomorrow.
Thank you.
Bye.